Lieutenant Yi here with lesson 24. We're going to do a quick touch on the power factor calculation, completing the power triangle, and then adding up complex powers. An important parameter of the power triangle is something we call the power factor. Now, it's going to have a variable name, it's PF, that's one variable, and let's talk about what it means. So if I have an example S, that's a complex power. We learned from the last lesson, I could break that up into the S component, which is the real power P in watts. I got to have the imaginary or reactive component Q in volt amps reactive. That hypotenuse or the length of the vector was the apparent power in volt amps, and I had the angle theta. Now, the power factor is going to be the ratio of the real power to the apparent power. So that is, say, how much of the apparent power is actually real. Okay, that's also, if you know something about triangles, that is the cosine of that angle. So that's an important equation. Both of those forms is the cosine of theta or P over the magnitude of S, or the real power over the apparent power, are important equations. So you also could predict that power factor is going to be limited to between 0 and 1 because that's the range of cosine. Also, though, it's not just a number. When I report the power factor, I need to state whether it is lagging or whether it is leading. All right, so this statement can be confusing because we're used to comparing waveforms that are between each other, say which one's lagging the other. In this case, there's an implied statement, and that implied statement is, what does current do relative to voltage? And we know that current lags the voltage for inductive circuits. So anything pointed up is going to be considered lagging. Anything pointed down, or the current leads the voltage, that is capacitive. So this example here, this top S, I would say, well, theta is positive, therefore it is a lagging power factor. Okay, so an example number would be that this is 0.7 lagging. That would be an example value of a power factor. And obviously I would have a power factor that is leading if I was down here. A common real-life representation of a load is actually not as an impedance, but as just a block and with some information about the power consumed, which means it's important for us to be able to use that information to complete the power triangle. So power triangle completion is an important skill that we're going to need to build up here, and there's only one way to do it, which is through practice. Okay, so if I take a look at load 1, I'm told that it consumes 1.21 gigawatts. I'm going to use this bit of information to start building that triangle. Pay attention to the units, because the units tell me that this 1.21 gigawatts refers to P for real power. I know that because it's watts and not volt amps. So I know that it's directed 1.21 gigawatts is just the X component. Now, if I look at the power factor, it tells me that it's 0.707 and that it's lagging. Immediately from that lagging information, I know that the angle is positive. This is important because if I use the equation that the inverse cosine of the power factor is the angle, I will always get a positive number. I need to use the leading or lagging statement to tell me. So if I did that, then theta is equal to 45 degrees. In this case, I know it's positive because lagging. And again, lagging means it's inductive, therefore think inductor is pointing up. So I know that the angle here is 45 degrees, and if you knew anything about 45 degrees triangles, then you could predict that this reactive part would be 121 giga VAR, and if you're really savvy, you would know to just stick this into your calculator. 1.21 plus J 1.21, take it out in the polar form, and you're going to get that apparent power is 1.711 gigavolt amps. So if I were to write the power triangle for load 1, I could write it either as S equals 1.711 angle 45 degrees gigavolt amps, or I could write it as 1.21 gigawatts plus J 1.21 giga VAR. Now you can do the exact same thing for load 2, but notice that load 2, they tell you a different type of power. They tell you the apparent power, 500 volt amps. All right, so also notice that this has a different description of the power factor. They call it leading. So I know that theta is negative for load 2. Okay, let's do the math. Inverse cosine of 0.6 would yield 53.13 degrees, and I know that that needs to be a negative 53.13 degrees because of the leading statement. That means it's capacitive. So I know that the angle is pointed down by 53.13 degrees, negative 53.13 degrees, and that the magnitude, that is the hypotenuse, is 500 volt amps. If you were to go and put that in your calculator, spit it back to yourself in rectangular form, you could extract the real power, where P is equal to 300 watts and the Q is equal to 400 volt amps reactive. Capacitive, that is, it would be negative. Okay, so the way you could express the S for this second load is that S is equal to 500 angle minus 53.13 degrees volt amps, or you could write it as S equals 300 watts minus J 400 VAR. Now that we can complete the power triangle, we can use it in a circuit like this, where we're going to start adding complex powers. Now, adding complex powers can be done without regard to whether series or parallel. Series and parallel don't matter. Power is power. If it's burning power, it's burning power. So the strategy here for a problem like this is you would find S of load 1, S of load 2, S of load 3, and just add them all up. So for example, S1 here, we know it's 1 kVA at a power factor of 0.707. Inverse cosine of 0.707 tells me that that is 45 degrees, and the fact that it's leading tells me that it's a negative 45 degrees. So I say that S1 is 1 kVA, angle minus 45 degrees. S2, I say that that is 5 kilowatts, 3 kVAR inductive, that's a plus J, 3 kilo VAR, and that's good to go. You say, well, you have polar and rectangular formats, both are good to go. You can add them in your calculator. So let's go ahead and complete number 3. They tell me it's 1 kVA and at an angle of, well, power factor of 0, and it's lagging, so it better be pointed straight up. 90 degrees. Inverse cosine of 0 equals 90 degrees, and it's positive because lagging. So if I want to find S total for the whole system, I could make that S total equal to S1 plus S2 plus S3. Notice this would be the same if I actually took the P components and said P total equals P1 plus P2 plus P3. I could also take the reactive components and say Q total equals Q1 plus Q2 plus Q3. The one thing I cannot do is add the apparent powers because the vectors aren't pointed in the same direction. All right, so once you get S total, the neat thing you can do with that is you can relate that to what happens at the source, where you can again pull out to that basic equation that S is times voltage times the current complex conjugated. So if you do that, remembering your RMS units, you could actually back out, well, what is this current here, as long as you were able to calculate S total. So again, you can add them all using complex numbers. Just enter in your calculator, make sure you're using S with the vector arrows, or you add up all the reals and all the imaginaries. All right, that's it for lesson 24. You can get the full version here or go to the next lesson here.